we are. This is CNET 40. Now, if you are here, you probably shouldn't be. Very few students are, because the job fair is happening right now. And if I'd known about this more in advance, and if it wasn't a short-term course, I would probably have canceled this class to encourage students to go to the job fair, but I don't think I can do that. So the students that are in this course, most of them, I imagine, are not attending live, but they're going to watch the video later. But the job fair is happening right now. I highly encourage you to tune in if you're interested in finding out about jobs in the area. Anyway, however, our topic is DNS security, and here we are. So I'm going to talk about DNS vulnerabilities and then demo the Google Cloud machines, because students have to make machines on the Google Cloud. And I added another extra credit project so you can make your Linux and Windows servers on the Google Cloud, because now we have these $50 Google Cloud certificates, which are nice. Although, if you have a credit card, you can get $200 or $300 of free service from Google Cloud anyway. But anyway, everybody, because of the certificates, should be able to use it, all the City College students. So let's take a look at that. What is what?
DNS proxy.
VSS?
DNS proxy.
Is it on this page somewhere? VSS? VSS proxy? Oh, I don't know, I guess.
DNS proxy.
EFF proxy?
DNS.
I can't hear the letters. DFF?
DNS.
ENS proxy.
DNS.
No, DNS proxy. Oh. Well, there's a bunch of these. These have been around forever. You can use a proxy server.
Hackers are using it to hide.
Well, I don't know why they'd be using it to hide. No, I don't understand that. I need to read an article or something to find out what they're talking about. I mean, all it does is proxy DNS request to somewhere else. I don't see how this hides you. Yeah.
Is the job fair in person or is it online?
It's online.
Okay.
Yeah.
Is it usually online?
It's been that way ever since the pandemic. It used to be face-to-face before that.
Is it ever going to go back?
I don't know. It'd be up to him. Steve Nelson's the guy running it now. Yeah. Sure, these are good. Very good. Anyway, so, all right, let me get the slides here. This is chapter 3, I think. There we are. Let's see if I already have them. 40, Black, chapter 3. I already have them. All right, good. So, all right, so DNS vulnerabilities. There's various things you can do to make your DNS system vulnerable. You can have bad configuration, bad architecture, and other kinds of weaknesses. So one simple one is making a single point of failure. This was true of many DNS companies' DNS arrangements maybe 10 years or more ago. You would just use a single server or go through a single switch or something, and then if that server goes down, then people cannot reach the servers at your company because they can't reach the authoritative server that would tell them their IP addresses. And if it's a recursive resolver, then your workers cannot get out because the outgoing DNS doesn't work. So that's why these days everyone's expected to have 2 DNS server addresses. So if one is down, you can use the other. That's why you have 2. That's the modern way to do it. And also, it might not be that you only have 1 DNS server. You might have 2 DNS servers, but they go through 1 router or 1 internet connection. And then, of course, if that goes down, that's the single point of failure and has the same results. So if all the DNS servers are at a single data center, then if the power goes out on that data center, you lose it. It's another way to have a single point of failure. And so the more critical your service is, the more distributed your servers should be. And as I mentioned, Cloudflare servers are fantastically well distributed and very resistant to attacks of all kinds. And the root of DNS is also very distributed and very resistant to attacks. You'd pretty much have to have the whole Earth be shut down before you take down the root of DNS or Cloudflare. So then there's other configuration errors. One really common one is the accidental exposure of confidential information. This is primarily because of Microsoft Windows. Microsoft Windows, the way it handles DNS is a sin and a shame, and it has been for more than 20 years. And one of the many really, really bad things it does is every time you boot up a machine, it automatically registers with the local DNS server. And often that server publishes that data to the world. So you end up exposing the IP addresses and DNS names of all your local machines when you didn't really want to. You have to be careful to avoid that on a Windows network. And then, of course, so that's one issue. And another issue is your DNS server might be attacked. That's one way to bring down a network. So here, This is a authoritative servers, and some site would be here, and here you'd have authoritative servers. Your authoritative servers should not be recursive. They should not be used for outgoing traffic. They should be used for external people coming into your company. And down here, you have public servers, a web server and say a mail server. And then you have non-public servers here. And the only thing in the zone files of your authoritative servers should be your public servers. You shouldn't have data about the other non-public devices there because there's no reason to expose that to external queries. All right. And as we already talked about last time, there are windows. You make a whole bunch of queries looking for local IP addresses on the internet as if they were public addresses, and that will therefore broadcast information about all the private addresses. You know when things boot up and you know what their IP address is. It's not only a burden on the DNS infrastructure at large, it's also an exposure of private information that is not good. And you can see this, of course. Here's the stupid queries we talked about in the last project. Trying to find 192.168.119 something as a public address, which is impossible and forbidden, but Microsoft is too stupid to understand that you shouldn't ask such stupid questions about DNS. All right, so you can fix this, as I mentioned in the setting up a Windows DNS server, if you tell it to be authoritative over those and fill in all the private address ranges, then it will not go looking for that information elsewhere. It will know not to do any reverse DNS lookups on those private things. That should be the default. Microsoft should have included that as the default in their software 30 years ago, but they forgot to ask for my opinion, and they don't seem to have learned anything in the intermediate time. All right. Then you don't want all your name servers to be recursive. Remember, recursive servers will go ask somewhere else to find things they don't know about. So they can tell you about every domain, like Yahoo, but for your authoritative server, it should not be recursive. It should only handle your domain and be authoritative and not try to handle anything else, because that's an unnecessary burden on it. You have separate recursive servers for your own employees to use going out to surf the internet. That's a different purpose than your authoritative servers. Now, a lot of people just have open recursive resolvers on the internet because they install DNS software and by default it's recursive and they don't turn it off and they just connect it to the internet. And then those can be used to attack other people. They're a risk to the internet at large because people can do a flood of queries to them over UDP with a target's address as the from address. So all the replies flood the target. So they can use them to create a flood of attacks against someone, and that'll appear to have come from the recursive resolver. That's why leaving an open recursive resolver is a poor practice for a company, and if you put one up, you're liable to get complaints from people that say your company is attacking me, and that's because somebody's using a recursive resolver as an attack tool. All right, so you should only accept queries from your own clients. Your recursive resolver should be there to help your own employees get to the internet. You should only accept queries from your own IP address range. That's a logical solution. You should not provide service to random people on the internet who are going to use it or be up to no good. If people need an open public DNS server, there are ones like 1111 and 8888 from companies like Cloudflare and Google that put up servers that are really open public resolvers, and they have put in defenses to notice if they're getting too many queries that are the same from the same IP address, they will block it. So you can make a powerful public resolver and design it to service the whole world, but that's probably not what your company wants to do. Your company would be better to just serve your own employees and let the big guys that want to do that job do that job. All right, so you can, there's openresolver.com is one of the places you can go to test to see if your IP addresses are open resolvers. All right. And all right, you can also do a dig, I think, to test it. Anyway, you manually test it here, you can use a form. You can use dig to test it, or you can use an online form to see if these guys have detected open resolvers. There's quite a few of these things. About 10 years ago, Robert Graham wrote a tool called MashScan, and this, as internet connections went up to gigabit, people realized you could scan the entire IPv4 internet in just like a day now. That didn't used to be possible. So MashScan is one of the first tools to do that, and people wrote a lot of tools that just scan the whole internet to find things like this. These guys just find all the open resolvers and make a list, and you can ask them if they're on the list. Anyway, so I tested City College servers this year, and they were all closed. This one, here's a test. If it was open, it would reply with open resolver detected. But I tested all of City College's ones, and it didn't reply, so they are not open. So we're not making that mistake. I wouldn't expect us to. You have to be pretty out of date to make that mistake. This is almost as bad as having an open mail SMTP resolver, which means anybody can send email through your network, and those used to be all over the place. And of course, spammers used them to send spam emails, so everybody shut them down, and very few people have those open anymore. Now, another thing you could do is zone transfers. And again, this is something that was true of Windows. When you'd install Windows DNS servers, by default, they would perform zone transfers to anyone. This is not a wise idea. Your DNS zone should not contain confidential data, but sometimes it does. And you just letting anybody copy the whole zone gives them information. It gives them your whole network map, essentially, of everything in there. And there's no reason to provide that information. It may or may not be a huge risk. It depends on how sloppy you are about letting machines register. But if you have a default Windows network and every machine registers your DNS server, now your zone file does contain a complete map of your local network, including a lot of machines that are not public servers, and getting the whole zone file will be a way to find that out. So you should only allow zone transfers to your other DNS servers and not to just random people on the internet. And this happened, by the way, recently to North Korea. The North Korean, in 2016, one of North Korea's top-level name servers was configured to allow global DNS zone transfers, so people noticed that and transferred the zone out. So that's the most recent example of anybody large making that mistake that I'm aware of. And let's try some Cahoots. Let me go to the right browser. All right. CNET 40, 3A, here it is. All right. How many people I have online. We'll see. What's that? What about this class? Can't, all right, hold on, let me turn, can't do what? Can't register for this class. Oh, if you want to, you have to use a late add form. If you want to actually officially enroll, then you have to go, let me get up here, go to my web page. Let me get rid of the, so go to samsclass.info, and there is a link here to a late add form. You have to fill out this form and email it to cnet.40@gmail.com. cnet.40@gmail.com. Yeah, yeah. No, cnet.40@gmail.com. Yeah, yeah, yeah. Good. Yeah, yeah. Fill out this form if you want to add the course. Good. All right. The form is here. Go to. Yeah, that's right. Let me go back to Cahoots. All right. Here's the Cahoots. The pin is 181.336. Good. Yeah. Good. All right. Yep. People are still coming in. This is fine. That's you, right, Luca? Good. Okay. All right. Well, let's try the Kahoot. See how it goes. Good. All right. So, which error can lead to denial of service? That's the point. Single point of failure means that single device can be taken out of service, and then people lose DNS service. All right. All right, which error exposes your whole network diagram? Zone transfers, yeah. Zone transfers are, now the internal queries just leak one record every time something boots up. You'd have to collect them for a long period of time, but a zone transfer will give you the whole diagram right away of everything that's registered in the zone.
Okay, but why does it get exposed? What if the zone transfer is like internal zone transfers?
Then it just reveals all the information to that internal machine, that's all.
Okay.
Yeah, yeah. That's right. Yeah, maybe I should say unprotected zone transfers or something would be a better thing to put there. It's a good point. That's why, part of why these things are extra credit, they're not entirely fair. And also, people can be talking and look, that's why this is all for extra credit. The real quizzes make more attempt to be fair. Anyway, all right. So which feature should never be active on a start of authority server? Recursion is not recommended. You could do it, but it's just an unnecessary burden on your authoritative server. Typically, you want 2 different servers to spread that load out. All right, what kind of server is a danger to other companies? An open resolver, like I said, that can be used to attack other people. All right. We got Sarah. Fred. All right. Fred and Joe. Okay, we'll get on the list. Greg, Fred, and Sarah. Okay, good. And this is 8:31. All right, so let's go back to here. Got plenty of time. All right. So another thing you can do, of course, is you might run your server process as administrator. This is something people often do because they have trouble with permissions and they can't figure it out. It's a poor idea, of course. Any web service providing service to people should run with low privileges because anything that accepts requests from the outside world is likely to get hacked. When you have a flaw, it will usually mean there is some kind of malformed request that can come in that gives the person control of that process, and then they get the privileges of that process. So you usually don't want to run anything as root, because then they only get limited privileges, and they have to go through a separate step of privilege escalation. And there are known privilege escalation exploits for every operating system, but you patch them and try to prevent those, and that's just more defense in depth. That gives the attacker more barriers to get in. Then, of course, there's whatever server software you're using is going to have vulnerabilities. Everything has vulnerabilities and patches coming out, buffer overflows, SQL injection, all different sorts of vulnerabilities. So if you go and look at ISC Bind, the #1 DNS server in the world, the original most famous one, it's had tons of vulnerabilities, although the really serious ones haven't been a really serious one in several years. Because, of course, they get better. The standards of programming improve, and after a while, they do clean out most of the bugs. In 2008, there was a severe vulnerability. The last one I could find that was big, which in principle might make it possible to execute arbitrary code. You could certainly crash the server and take it down, and they thought you might be able to also execute arbitrary code. So that's a pretty severe one, but that's getting to be quite a whiles back. Now, source port randomization is a defense almost every DNS server has now, and this was what made Dan Kaminsky famous, was the 2008 cache poisoning attack. So I'm not going to play the video because this is getting pretty old and not really that important, but you should understand why this had to happen. Originally, DNS servers always used port 53, not only as the listening port for external queries, but as the source port for responses. They would come from port 53. Now that might seem harmless, but it's not, because of another design flaw in DNS. When I make a DNS query to a server, it's UDP traffic. Then UDP packets come back. They're not tied in any way to my request. Now, if it was TCP, I would do SYN, SYNAC, ACK, and then we'd have a channel of communication where I send a request, and when the reply comes back, it's part of the same TCP stream, so I would know that that reply was in response to my request. But DNS uses UDP, so if I send out a UDP request to like yahoo.com to get an IP address, then 100 other requests come in the same second, then a bunch of traffic comes back, I eventually get a packet back that tells me Yahoo is somewhere. How do I know that that was a response to my request? That could be some other traffic flying around, and there's no way to connect it. And the only way to connect it is the TXID, which is a 16-bit supposedly random number. Although I think early versions might even use sequential numbers there so you can predict them. But anyway, that's the point. Yeah, bind 8 and 9 use predictable transaction IDs. So the port number was always the same, and the transaction ID could be predicted, so you could easily spoof a reply which would appear to have come from the server and appear and be indistinguishable from the real reply. So that's bad. And so you can see it happen. Nowadays, the transaction ID is random anyway. You can view a few of them in Wireshark, and you can make a column of the transaction ID, and you'll see here's the query and the response with the same transaction ID of C668, then this one, then this one. Each time I make a request, it has a new, fresh, random number. That's the way all modern DNS servers work and DNS clients. However, even that is not enough, and that's now they thought that was probably fine because there's 65,000 possibilities. And so a bad guy would only have one chance in 65,000 of guessing that number. But that turned out to not be true, and this is what made Dan Kaminsky famous. You can make like 500 guesses at a time if you plan your guess maliciously enough. So here's what, now, if you run a domain with a start of authority you control, then you send the target an email with a link to server.evil.com and hope somebody clicks on it. Now, their machine will try to find this server name, and they will have to ask your DNS server, does it exist? So I can trick people pretty easily into making a DNS request from a DNS server I control. Now, what I can do is CNAME chaining. I can make this a CNAME for this, and this a CNAME for that, and this a CNAME for that. So the first query will cause the recursive resolver to make another query and another query and another query until it has to do a lot of queries just from one link that was clicked somewhere. And each link can put additional information in the response. So I can do, this has start of authority. There's other ways to make delegates. I just can delegate the query to a different name server, and this can delegate it to a different name server. So again, I can trick this original request into provoking a flood of more requests. And then the protocol design had weaknesses. So the point is, each one of those replies can contain a lot of information. Anyway, so here's the elements to match it. Transaction ID, question, source and destination IP, source and destination port, but the request destination port is known to be 43, and the client will just take the first response that meets these criteria, and if it is a caching resolver, which most of them are, it will save the result in the cache and not check again for a long time. So if you get the false data in there, it will redirect a bunch of traffic to go to the wrong address for quite a long time. And so that's what DNS cache poisoning is. So somebody, the target, is trying to go to Yahoo. They ask the resolver, where is Yahoo? It doesn't know because it's not the Yahoo authoritative resolver, so it's a recursive resolver. So it goes and asks somewhere else, where is Yahoo? From the real Yahoo server, but the attacker replies with a forged response that gets in first and tells it the wrong address for Yahoo. It now caches that for as long as you told it to keep it, because in the reply you told it what the cache lifetime is, so you could give it a cache lifetime of a week. So now it'll just, for a week, for all the clients will get told the wrong address for Yahoo. Then you put a fake Yahoo page there, you get their credit card numbers and stuff. That's how it works. And Dan found a way to connect a whole series of requests so there were many, many guesses at the transaction ID in each response. So he was able to guess like 500 different numbers from one query. And now that you're guessing 500 at a time, guessing the right one out of 65,000 is not that impossible at all. And so he was able to successfully poison real name servers that affected the internet in a large way, and he told people and got it fixed. So anyway, that's the famous Kaminsky attack. And there's a lot of ways to do this. Here's another way to do it. You can make a web page that just has a whole bunch of images that all go to your evil server under your control, and that'll make a whole bunch of DNS requests up there. There's just so many ways to trick a web page into making a lot of DNS requests. All right, so you can sometimes poison in as few as just a few seconds. Now, another one is if you have a privileged position, if you're actually in the middle between the target and the resolver, which you could easily do if you're in a Wi-Fi coffee house, you can use art poisoning to put yourself in the middle. Now, you're pretty much hosed because I can read everything about your query and craft a malicious response, and there'll be no way for you to prevent this. This is why now the source port randomization was used to add another 16 bits of randomness to this. This was the effective fix for this problem. To prevent this poisoning, now the reply has to not only have the right transaction ID, it has to originate from the correct source port, and the source port from the server is random. So that was the trick, and that means that's why now I have to guess 32 bits, and even if I can guess 500 at a time, that's impossible. So that is the modern solution. That was the first solution to patch the problem with a minor change without breaking the protocol that would make it much more difficult to do the Kaminsky cache poisoning attack. But in the long run, the solution is DNS Sec. With DNS Sec, the server has a cryptographic signature that you can verify to prove it really did come from that server and nobody else, and the attacker can't forge that. So that's the perfect solution. All right. And so that's the real cure for this was DNS Sec, but the temporary cure to get us through the last decade or so, really is still the main one employed, is random source port IDs, which lower the chance of attack by another 65,000, and that's enough to make the attack risk low enough that nobody really cares anymore. Anyway, the other one I mentioned before is DNS could be a DOS amplifier. If you have an open resolver, an attacker can send packets here, and then the target gets a flood of packets from here and blames this guy for it, and the attacker is scot-free. None of those packets contain the attacker's address anywhere. So this is really quite effective, and there's a whole lot of those attacks out there, packet amplification attacks.
How
Yeah.
can this happen, the amplifier?
What's that?
How can this happen?
This happens anytime you take any UDP request and the reply is larger than the request. So all you have to do is make a reply with a large response. DNS can have a response that's 50 times bigger than the request. NTP can be 100 times bigger, and there's some other protocols that are like 500 times bigger. Anytime it's based on UDP, the two flaws are you have a reply bigger than the request, and you use UDP. Because I have to forge this, I have to lie about the from address of this. And if it was TCP, that would not be possible, because I couldn't complete the handshake. That's why, you could argue that UDP is just a bad idea, but it's much more efficient. You can service much more requests per second over UDP than TCP. That's why people use it, but the penalty is security. So the correct thing to do is you should do rate limiting. You should notice if you're getting a lot of identical requests from the same address and refuse them. That's the correct defense against this, and that's what those big open resolvers do. All right, let's try another Kahoot. Here. All right. I think that's best current practice 38 or something. There's RFCs for internet standards, and there's BCP documents for recommended procedures. And one of them is rate limiting multiple requests. Yeah, I think it's BCP 38 or something. I used to know the number. Everything on the internet, there are these documents, either RFC documents or BCP documents that are like the official standard. And might be 23, might be 32, something like that. See if I can make my object get smaller. There it is. People can still see those numbers. Let me try to find it here. BCP, maybe 32. Can't find it. Yeah, here we are, information on BCP 32. Reserved top-level DNS names. I guess it's a different number. Yeah, reserved, but I might be able to get a list of these. What's that?
You are rating the response like that?
Writing things with
You are rating the response?
rate limiting the response. Yeah, that's right. Rate limiting the response. If you get, this one here is different. It must be one, maybe 23 or something. I forget the number. There should be a list of them somewhere. There we are, BCP index, there we are. There they are, okay, good. So it's not a very high number. Keywords, deployment of internet web pages, use of aliases, a useful thing to know about. This is basically the Bible of the internet, these documents. And someplace is one here, anti-spam recommendations for SMTP, reserved DNS names, change the default for directed broadcast. That was what stopped the ICMP flood attacks. And someplace down here, one of these network ingress filtering, that's it, 38. Network ingress filtering to defeating denial of service attacks, which employ IP address source spoofing. That's the one, BGP 38 is the one you should use for a public resolver. Anyway, good. All right, I think people are in. Let's give this a shot. Okay, so what weakness makes it more dangerous when your server gets hacked? Okay, running in privileged mode is correct. I see a question in the chat. Does it mean for most ports, including 8443.22, we can either use TCP or UDP for sending the packet? No, I think not in general. When ports are reserved, they do reserve both the UDP and TCP port for things, but I think most of them use only one or the other. Like most DNS servers use only UDP, although some of them are now switching to TCP to handle the DNS sec. I don't think you can use UDP at all for SSH. You have to check the protocols. Some of them do use both, but in general, no, not in practice. In practice, most of them use just one or the other. All right, so what weakness makes it easier to poison your cache? Fixed source port, but if your client doesn't use a source port of 53 but uses a random source port, then that's another 16 bits of randomness to check in the reply to make sure the server really heard you. So, all right. All right, what attack causes all the users of a server to see fake websites? All right, that's cache poisoning. If you can change the stored data on the server, then everybody that uses that server will be lied to for a period of time. All right, what attack exposes information but doesn't cause any other immediate harm? As to zone transfer, you see information, but you don't poison the cache or anything. You don't change any actual resolution that anybody gets. You just learn information that wasn't probably intended to be public. All right, what attack lowers availability but does not affect confidentiality or integrity? These are, of course, the three aspects of security. That's DOS. You deny access to the server. That just means it's no longer available to some people, but it doesn't have any other effect on it. All right. All right, what attack lowers integrity but does not affect confidentiality or availability? That's cache poisoning. You have been unauthorized alteration of data. You've changed data on the server when the only thing that should be allowed to do that is the real SOA server from somebody. You haven't done anything else, but you made it believe a lie, and that's integrity. That's violating the integrity. All right, so. Luca, all right. TCL have rules, okay. Stop recording. And the recording goes.